Calcium is needed in the body for muscle contraction. The ATP binds to the myosin, making it detach from actin. The ATP then turns into ADP, releasing energy to convert myosin heads into a cocked state. The calcium then binds to the troponin, which exposes sites on the actin which the myosin can bind to. Calcium ions are released from a structure in the cell known as the sarcoplasmic reticulum. The myosin then completes a power stroke, pushing on the actin, and this process starts again. During muscle contraction, calcium ions are released into the cell, causing filaments in the muscle fiber to contract. During muscle relaxation, calcium ions are pumped into storage, allowing the muscle filaments to relax. Entire muscle channels leak calcium ions. This weakens contractions. There are four main ways that the body can become fatigued. Depletion of all ATP and PC stores, myoglobin has lost all of its oxygen, glucose and glycogen stores have depleted, or the body has accumulated high levels of lactic acid. If muscles continue to be contracted in the same way, there is a point where the body becomes physiologically unable to contract, even though the muscles are still receiving the signals to contract. The first reason for this is that the muscles run out of energy. ATP is the main energy store inside of the muscles, and even when our muscles fatigue, they still contain small amounts of ATP. This suggests it is unlikely that the muscle has run out of energy. A second reason why could be because of a buildup of waste products like lactic acid. Because lactic acid increases the acidity of the blood, it impacts the calcium released from the sarcoplasmic reticulum. This could cease muscle contraction. However, muscles have been found to usually contain an acceptable pH limit. The third reason that could be stopping the muscles from contracting is the disturbance of excitation-contraction coupling. If somewhere between the brains to the nerves or directly at the muscle junction there is something inhibiting the pathway, then contraction will be blocked. Impulses of these nerves are affected by sodium and potassium and shown on the screen. Sodium rushes inside the nerve cell during an impulse, and potassium rushes outside of the nerve cell to help prepare it for the next impulse. Before the next impulse, though, the nerve must reset, and it does this by pumping sodium back outside and potassium back inside. If some of these sodium or potassium ions float away, it means that there is less sodium or less potassium for the next impulse, and so on. Eventually, the nerves have lost the ions that they need to reset, so our brain sends these signals to contract, but our muscles never receive these signals. Acetylcholine is required to transfer the nerve impulse across the synaptic gap at the neuromuscular junction and initiate muscle contraction. Muscles work through the all or none law, which means if there is enough ACH, a contraction will happen, and if there isn't, then none of the fibers will contract. If insufficient ACH arrives at the receptor sites, muscle contraction cannot proceed and fatigue occurs. Cholinesterase is an enzyme that breaks down ACH after this role and prepares it to be used again. For another muscle contraction to begin, the synaptic cleft has to be cleared first of ACH by the enzyme cholinesterase. When there is excess ACH or lack of cholinesterase, fatigue results from the inability to generate a new action potential. Early studies from Scandinavia showed that carbo-loading, a technique used by athletes, can improve endurance exercise performance in events lasting longer than 90 minutes, found by Hawley et al. 1997. Muscle glycogen availability is also important for the maintenance of high-intensity intermittent exercise, Balsam et al. 1999. The process of carbo-loading starts around 7 days before a big event. An athlete will choose to keep continual training, but they will eat significantly less carbs than usual in order to deplete the body's glycogen stores. In the graph, this is shown in days 1 to 4, where the athlete's glycogen stores have decreased from 90 to around 20. In around 3 days before the race, they then consume maximum amounts of glycogen and stop exercising. At the end of day 3, the body will think that there is a problem with its glycogen stores, and that when it next can, it should store more glycogen than usual. On the graph, it can be seen that these muscle glycogen stores then continue to increase to 150. A study conducted by Metab in 2012 found that novice and recreational marathon runners should consider consuming a moderate to high amount of carbohydrates in the 24 to 36 hours prior to a marathon to improve their performance time. Carbo loading also helps athletes who run endurance events such as marathons avoid hitting the wall. It is sudden fatigue and loss of energy which is caused by the depletion of glycogen stores in the liver and muscles. This usually happens around the 18 to 20 mile mark or after around 2 to 3 hours. The body cannot physically go on running any longer. Saving glycogen stores during carbo loading is known as glycogen sparing, and it stops the body from being overcome with this painful fatigue. Glycogen sparing is also a good way of training an athlete to burn more fat and to burn less of their glycogen stores. Glucose is the key substrate for the brain to keep fueled. Therefore, having low amounts of glucose in the blood, which is known as hypoglycemia, may also reduce uptake of glucose into the brain, which could contribute to central fatigue. This was discovered by Nybo and Seisha in 2002. After glycogen stores have been depleted and before gluconeogenesis kicks in, an athlete may experience symptoms of hypoglycemia. They may feel extreme fatigue and a near complete loss of energy. This is often referred to as bonking or hitting the wall as previously spoken about. It may result in other symptoms including clumsiness, trouble talking, confusion, loss of consciousness, collapse, seizures, or even death. It is thought that pre-cooling in hot environments will improve endurance exercise performance by lowering an athlete's preliminary core body temperature, thereby increasing the margin between the initial core temperature and temperatures at which athletic performance is affected. Athletes can often do this by drinking slushies or wearing cooling up vests with ice in them. A study using athletes that completed pre-cooling, preheating, or neither proved that pre-cooling allowed athletes' body temperatures to remain low and exercise for longer. Obviously, the preheating group tired out the fastest, and this was not an effective method. This is another way athletes can avoid becoming fatigued. Hydration for athletes is very important and involves making sure they drink enough fluids before and during an event. The body produces 10 times as much heat as running as walking, so during events like marathons, it is very important that athletes stop to drink water. If an athlete does not drink enough water or fluid, it may cause a reduction in blood volume, decreased skin blood flow, decreased sweat rate, decreased heat dissipation, increased core temperature, and an increased rate of glycogen use. This then causes them to fatigue much faster and give a poorer performance. Dehydration causes strain on the heart because the blood thickens and the vessels thin. This is known as viscose. The amount of blood circulating through your body decreases when you are dehydrated. To compensate, your heart beats faster, increasing your heart rate and causing you to feel palpitations. The graph on the right shows the difference in an athlete's performance when they drink fluids compared to when they don't. Both athletes worked for 2 hours, but the one who drank fluid had a much lower rectal temperature, meaning that less of their blood would have been circulated to the skin's surface, and they would have been able to work much harder. The graph on the left shows that athletes taking water and carbs perform at a higher maximal power than those that drink just water or just eat carbs or neither. Active recovery is key in how we recover from an athletic event. It is beneficial to athletes in a number of key ways. It reduces the buildup of lactic acid in the muscles, minimizing post-exercise stiffness and discomfort. It helps alleviate fatigue and improve moods that typically crash after a heavy sporting event. It promotes blood flow to the joints and muscles, counteracting inflammation. This is because during exercise, the skeletal muscle pump works hard to pump the blood up towards the heart. When this muscle contraction is stopped, then the skeletal muscle pump can no longer help to push the blood back to the heart, and it causes venous pooling. It maintains the heart rate at a more steady state, improving endurance and training volumes. Depending on the type of exercise, depends on how long your body takes to fully recover. For example, after a shot put through, though the body only needs to replenish 3 seconds worth of ATP stores, however, after a 26.2-mile marathon, the body needs to replenish all of its ATP, PC, and glycogen stores, as well as remove all of the built-up lactic acid in the muscles. After an event like the 800 meters, the body will have only used its lactic acid system, meaning there will be a lot of lactic acid buildup in the muscles compared to the submaximal marathon. Recovery is not an instantaneous effect, and the body can take up to 8 hours to recover. When we damage the muscles, it can take anywhere from 24 to 48 hours to recover. Essentially, recovery is how the body restores its body systems to resting levels, resynthesizes its energy system, and repairs the damage done to the body. EPOC is excess post-exercise oxygen consumption. It refers to breathing fast and deep following exercise to help increase the amount of oxygen in the body to return the body back to its pre-exercise state. Part E of the graph shows the oxygen deficit. Part C then shows the oxygen consumption, which is the amount of oxygen that the body does get to take in during exercise. Part A and D demonstrate EPOC, as it is the oxygen consumption after exercise has stopped. Part A being the fast component, or alactacid det, and Part B being the slow component, or lactacid. Finally, Part B refers to the resting levels of oxygen consumption. EPOC changes on size depending on the length and intensity of the exercise. Submaximal exercise has a smaller oxygen deficit and mostly aerobic respiration, meaning less lactic acid and a quicker recovery, whereas maximal exercise has a larger oxygen deficit and mostly anaerobic respiration, meaning the accumulation of more lactic acid. This results in slower recovery. Oxygen deficit refers to the difference between oxygen intake of the body during early stages of exercise and during a similar duration in a steady state of exercise. In other words, it is the amount of oxygen the body needs but it doesn't get. It is a temporary shortage of oxygen during exercise unless all of the energy contribution is from the aerobic system. The volume of oxygen has to meet the demand of a specific activity. In the graph on the screen, it shows that as somebody begins to exercise, their oxygen consumption increases slowly, which is to be expected, as when we begin exercising, we do not start by using our aerobic energy system. The striped part of the graph shows that the lactic acid system is being used and glycogen is being used up, as this happens before we take in enough oxygen, as the aerobic system is complex. The alactacid stage of recovery, sometimes referred to as the fast component of the EPOC, happens within the first 2 to 3 minutes that exercise has stopped. It requires an additional 1 to 4 litres of oxygen, and it has 3 main jobs. These are to resaturate myoglobin with oxygen, resynthesize the ATP stores, and to resynthesize the phosphocreatine stores. 50% of phosphocreatine is resynthesized within 30 seconds of when exercise has stopped. If the previous exercise completed is a short bout of intense work such as a maximum lift or 100-meter sprint, then the body should be recovered enough after 3 minutes to repeat this exercise. Lactacid recovery happens after alactacid recovery. It is known as the slow component of EPOC and it is a much longer process. It is given its name as it is the removal of lactic acid from the body. The lactic acid has accumulated due to the anaerobic work that has been done. Most of this lactic acid is removed into the blood or oxidized in the mitochondria via the aerobic system with oxygen to give carbon dioxide and water. It is converted back to pyruvic acid to be used again in the Krebs cycle. Lactic acid is also converted into muscle and liver glycogen, glucose, and protein, and some of it is removed from the body as sweat or urine. Specifically, 65% of carbon dioxide water, 20% is glycogen, 5% is glucose, and 10% is protein.